Hello and welcome to this video on special right triangles. We're going to start by looking at a rectangle diagram in front of us to explore the parts of this topic and then kind of set out the rules in notes and then look at examples together. So for starters, we have a rectangle in front of us with some information provided, but most of the rectangle is left blank. So we have a kind of all 90-degree angles in all the corners. We have a 30 and 30-degree angles there. And then we also have basically a lot of angles missing. So our goal eventually is to figure out the length of segment BD and the length of segment AD, given our two angles here and given that we have a 5 right here. So the first thing I would do is try to fill in as many missing angles and sides as I can right away. First, I know that we have a rectangle, so across from our 5, we also have a 5 right there. Next, we have a 30 and a 30-degree angle there, so there would only be 120 degrees left over in this triangle for that angle right there. And that means that we have another 120 degrees at the top of that angle because those are vertical angles. We can fill in these two angles on the sides right here because those are supplementary, to our 120-degree angle, giving us 60 degrees and 60 degrees right there and there. Continuing on, we also have some complementary angles, like this 30-degree angle will give us this 60-degree angle right here. So we can fill in this as 60 degrees. And since we have a triangle on this left side, that means that the angle missing here is also going to be 60 degrees. Right there, and then we can do basically the exact same thing to the triangle across the way. So we have a 60-degree angle and a 60-degree angle. And that's as far as what we need, as many angles as we need to fill in. So what we can go from here to proceed is that these two triangles on the left-hand, right-hand sides, those are both equilateral triangles. If all of your angles are the same, that means that all of your sides also have to be the same. What that means is that we can label these sides of the triangle each as 5. And then we can do the same thing on this other triangle across the way, 5 and 5. Right there, by using just vocabulary and what we know already, we have figured out that segment BD is equal to 10 because we have 5 and 5 adding up to that. So BD is equal to 10. Now we need to figure out what AD is on the bottom. So now there's a couple different approaches to this, but what we want to use as the kind of main approach is that we now have a kind of right triangle that would include the 3 that we have here. So we have segment AB. We just found segment BD, and we're looking for segment AD. So I can make a right triangle off to the side of my rectangle, where this triangle, or this triangle would be triangle ADB, where our right angle is at A. And we know that we have a 5 for that left-hand side, and our hypotenuse would be a 10. Now we have a right triangle with two sides that are known, and that means we can do Pythagorean theorem. So to find AD, we would need to do 5 squared plus AD squared equals 10 squared. So if we do 10 squared is 100 and 5 squared is 25, so that means if I subtract 5 squared from both sides, I would find that AD squared would be 100 minus 25, which would be equal to 75. Now, if I take the square root of both sides, I figure out that AD is going to be equal to the square root of 75. But we can't leave that like that. We know we can simplify square roots. So if I come up here to the top corner of my page, I can write the square root of 75, and I'm going to use our tree method to simplify the square root of 75 to something that is more manageable. So if I break that into a tree, I have 25 and 3 as factors, and then I can break down 25 into 5 and 5. That means, as you probably have guessed, that our triangle, our square root would simplify to 5 times the square root of 3. So we've now figured out that AD is 5 times the square root of 3, 5 times the square root of 3. And on this triangle we just made, we can also fill in some angles. Like we have a 30-degree angle and a 60-degree angle. And this is going to demonstrate the pattern that we're going to be looking for. So you can see that we have a 10 for our hypotenuse side. Now that is going to be the biggest side. The side opposite from 30 degrees is half of what the hypotenuse ended up being. So the 30-degree side is 50, or 5, I mean. 50% of the hypotenuse side, that is. And then the side opposite from 60 degrees is 5 times the square root of 3. And that opposite from 60 degrees, so we can draw some arrows here maybe. So you can see the 60-degree side was 5 root 3. The 30-degree side was 5. The hypotenuse side was 10. So our hypothesis here is that first, the 30-degree side is always going to be half of our hypotenuse side. And the 60-degree side would be basically root 3 times bigger than our 30-degree side. In other words, the square root of 3 we know is equal to about 1.73. So what we're saying is that the 60-degree side is about 1.73 times bigger than the 30-degree side, which is interesting because obviously 60 degrees is double what 30 degrees is, but the 30-degree side is, if you double the 30-degree side, you don't get the 60-degree side. If you double the 30-degree side, you actually get the 90-degree side, or the right angle side, which is kind of contrary to what you might guess. So basically, if we kind of adapt that to a general version, we can kind of fill in, if we kind of move down our page here. So we have this rectangle that looks the same, so we can mark X where that 5 was, and we already established that we have all these angles filled in from before, so we're going to have an X and an X here, and we basically can just replace the things we have, so we can have an X there. So if AB, our 30-degree angle, is X, we can kind of write our pattern as opposite from 30 degrees would just be X. Opposite from 60 degrees would be X times the square root of 3. And then opposite from 90 degrees would be 2X. And this is a pattern that is actually true in all right triangles that are the same angles as these. And the name for it is not very clever, but these are called 30, 60, 90 triangles. And the pattern that their sides follow will always follow this right here. Now we can grab kind of a bigger picture of this pattern right here. So this is where you really want to be taking this down in your notes, because we have a example of just basically across from 30 degrees is just A. Across from 90 degrees is double that, or 2A. And across from 60 degrees is A times the square root of 3. Show an example here where you're going to need to remember how to simplify square roots like we did earlier, and also be able to kind of solve some equations here, which you'll see in the examples we're about to start right now. Now, in these examples, we could use trigonometry functions in order to solve for these answers, but we want to basically use these patterns to allow us to not have to do that, so that we'd be able to get to our result a lot faster. We're now going to start on the 6 example problems that we'll be working through right now. So in number one, we want to fill in our missing angle as 60 degrees first. And then we want to basically label our triangle with our pattern so we can use it to solve for the two missing sides. So our 30-degree side is opposite, that is our A. So we already know that our A is equal to 12. Our hypotenuse would be 2A. So that means that 2 times our A of 12 would make that into a 24 for our hypotenuse side. And since our 60-degree side is going to be A times the square root of 3, we can label that as A root 3. And then, well, if we know that A is 12, that means that we are going to have for our last one a 12 times the square root of 3. And we can show there, right, we're showing there that how easy it is to find these missing sides. Moving on to number 2. So in number 2, like before, we want to fill in our missing angle of 60 degrees. And we want to label what all these sides are. So based on our pattern, so our 30-degree side is A, our hypotenuse is 2A, our 60-degree side is our A times the square root of 3. Also, these are not to scale, even though it looks like the 60-degree side is shorter. We're just going to not worry about that right now. So we know our 2A is equal to 16. So it's kind of like you're solving 2A equals 16. That means that A has to be 8. Simple as a linear equation like that. So now we know that A is 8. If A is 8, that means that A root 3 has got to be 8 root 3. So not even that much math right there that we were doing in number 2 just now. So kind of continuing on with that, similar to a problem in number 3. Like before, we want to label our missing angle as 30 degrees. And we want to label our pattern on our triangle as A, 2A, and A root 3. So here's a little bit different in that we're showing that 10 root 3 and A root 3 are equal to each other. Well, if you take out the root 3 from both sides of that equation right here that I just wrote, well, that means that the 10 has to match the A part, just like how root 3 matches itself. Meaning that A is equal to 10. To get 2A, we just got to double it. So that would end being 20 for our hypotenuse side. And we can put those different colors, 10 and 20 for those two missing sides. And that's really following the same thing, but in each of these problems, we've kind of seen a different thing that we're starting with as given information, and we can have that as what we're using to go forward. Number 4. So number 4, we have a rectangle like what we started with, but we don't care about the lengths in the other triangle, and we'll figure those out at the very end. So we know that we have a 60-degree angle here, and we can label in our sides of our pattern. So our A is that 7 across from 30 degrees. Across from 60 degrees is A root 3, and then our hypotenuse is 2A. We got our pattern. Following that pattern, if our A is equal to 7, well, that means that 2A has got to equal 14. If our A is 7, A root 3 has got to be equal to 7 root 3. Since we're dealing with a triangle, opposite sides of a rectangle are now going to be equal to each other. So we know that this side is 7 across from another 7, and the top is 7 root 3. So before we go and try number 5 and 6, we're just going to work a little bit different just to prove to ourselves that all of these patterns are still working out how we want them to. If I take, say, the number 3, and I need to know, well, is 10 root 3 squared plus 10 squared equal 20 squared? Or we'll use 4 since we're looking at it. So I would need to show that 14 squared is equal to 7 squared plus 7 root 3 in parentheses squared. So if I get a calculator here, I first can see what 14 squared is. Well, that's 196. 7 squared plus 7 times the square root of 3 squared equals 196. And we've proved it with our pattern works for that triangle. So now let's move on to our more challenging problems in 5 and number 6. They're both kind of similar, and you'll see why in a second. So number 5, we have a 30-degree angle up at the top. And so we're starting the same way and then putting in our pattern of A and A root 3 and 2A. So right away we see that our hypotenuse side has a root 3 in it, which is not what we've seen so far. So what we need to basically do there is establish that, well, I can still solve for A. So if I was dealing with this equation right here, if I want to know what A equaled, I would just divide both sides by 2. So if I know that I have 26 root 3's, well, that means that 13 root 3's would be half as many. It's like having 26 apples, half of that is 13 apples. In this case, root 3 is the apple. Well, now we know what A is from what we just wrote. That means that our A down here is also 13 root 3, since we just figured out what A was equal to right there. Well, now, if I need to figure out what A root 3 is, and I know A, well, that means I would basically be doing 13 root 3 as my A, and then multiplying that by root 3. So you could do that on your calculator. So let's show that first. So if I was doing 13 times the square root of, what was our square root of 3, and I'm going to multiply that by another square root of 3, it equals 39. That's because root 3 times itself, the square root of 3 times itself, that is equals 3. That cancels out. When you're squaring a square root or multiplying by itself, they disappear. So that means that our A root 3 part of our pattern would end up being 13 times 3, or 39. And you can see it's basically once you have the pattern set up, you're just solving for A and then using that in all 3 parts. So that's a good one for our notes for sure. Let's move on to our last example problem now. So we have number 6. Like before, fill in our missing angle of 60 degrees and then fill in our pattern. Across from 30 degrees is our A, 60 degrees is A root 3, hypotenuse is 2A. Now, we have our A already. So right there, that should make things easy. So now if we double 11 root 3, that would basically be just doubling the 11 part, because we have 11 of these root 3's. If we double that, we would have 22 of them. So that means that 2A would then have to be 22 root 3 as our exact measurement there, because we just doubled 11 root 3. 11 root 3 times 2 equals 22 root 3. 22 root 3. And then lastly, if I need to do A root 3, well, if I know that A is 11 root 3, well, that means I do 11 root 3 for my A. That's my A value. And then multiply that by another root 3. Like before, root 3 times root 3, that equals just 3. So I'm really just doing 11 times 3, and that equals to 33. So we have now shown how to find all of these examples in our problem here. So let's zoom out on our camera here, back to our regular zoom, and look at our bottom of our page here. So as far as our pattern goes, well, we are going to basically, in order, have A is our 30-degree side, A root 3 is our 60-degree side, and 2 times A is our 90 degree side. For which side of the triangle is always half of the hypotenuse? The 30 degree side is always half of the hypotenuse. And this is something that can be confusing because the 30 degrees is half of 60 degrees, but the 30 degree side is not half of the 60 degree side. It is 60 degree side is smaller than half. Our 30 degree side is larger than half of the 60 degree side. But if that's confusing, we already answered number 2. 30 degree side is half of the hypotenuse. Now, the number 3, why does it make sense for the 30 degree angle to be A? Well, when you have any triangle or any triangle, the smallest angle is going to create the smallest side as long as you kind of follow along the 2 parts of your angle. So the 60 and 90 degree sides are going to hit larger sides. The 30 degree side is going to hit a smaller side. And that would be the reason why. So the 30 degrees is the smallest angle leading to smallest side. And that kind of covers number 3. So we've already kind of answered number 4. In number 5 and 6 above, the side opposite 60 does not have a root 3. If you were given the length of the side opposite 60 and did not have root 3 attached in these problems, how could you find the lengths of the other 2 sides? The easy way to think of it is in 5 and 6, we know, for instance, like 39, a root 3. We're just basically just solving it for A so that we can figure out what A is. Like here, we know that 33 is that one. So, for example, if I knew that, say, my 60 degree side was equal to 30, well, that means that A root 3 has to equal 30. And if you knew that, well, that means you just have to divide both of those sides by root 3. In later math class you'll have to do what is called rationalizing. And at least for us, we're not going to need to worry about that in math 2. Suffice to say, that would be our answer. And that covers everything you need to know about 30, 60, 90 triangles. Next time in our next video, we will be covering the other type of special right triangles, and I will see you all then. Thank you for watching.